The ocean planet model was initially proposed by the New Zealand astronomer David J. Stevenson of the California Institute of Technology, Caltech, at the turn of the 21st century. This model was then further developed by the team of Christophe Sautin, planetologist and professor at Nantes University. At the origin of the discovery of ocean planets, there is the phenomenon of planetary migration. We speak of planetary migration when a planet moves closer to its star after its formation. This theory was developed to explain the discovery of gas giants too close to their star to have formed there. The first ocean planet was discovered by calculation on December 16, 2009. It was named GJ1214b, or Gliese 1214b, and is located in the constellation of Serpentarius at about 40 light-years from the Sun. We will explore this ocean planet a little later in this trip. But then, how did astronomers come to the conclusion that the ocean planets of science fiction could really exist? Since the middle of the 20th century, even before the discovery of the first exoplanet, important discoveries have been made concerning the presence of water in the universe. In particular, scientists looked at the moons of Jupiter and Saturn. In the 1970s, NASA scientists became interested in Ganymede, a moon of Jupiter, where they suspected the presence of a thick underground ocean sandwiched between two layers of ice. Lewis's work showed in 1971 that radioactive decay could, especially in the presence of ammonia, produce underground oceans in large moons. The search for water on Mars has also been the subject of numerous studies and space missions. Since the first exoplanet was discovered, astronomers are now looking for evidence of liquid water beyond our own solar system. In 2004, Alain Leger, a researcher at the Institute of Space Astrophysics, calculated with his team that a small number of icy planets formed on the outskirts of their star could migrate inwards by up to 1 astronomical unit, the distance between the Earth and the Sun. This migration would melt the ice of the outer layers, forming ocean planets. Today, the existence of ocean planets is no longer a simple scientific hypothesis. Observations from the Hubble telescope, as well as information gathered by space probes such as Galileo, Pioneer, Voyager, or Cassini-Huygens, indicate that several bodies in the universe could harbor liquid water under an insulating shell of ice. But not only. Because the model of the typical ocean planet can vary depending on multiple factors, including the composition of the atmosphere. In June 2020, NASA scientists asserted, based on numerical models, that it is likely that ocean exoplanets are common in the Milky Way galaxy. The first potentially habitable ocean exoplanet was discovered just recently, in June 2022, by the Transiting Exoplanet Survey Satellite. It was named TOI 1452b. Like Gliese 1214b, we will explore it later in this trip. In the meantime, we will discover why ocean planets interest scientists so much. We now know that ocean worlds most certainly exist, even though there is no direct evidence for their existence. Why has this discovery been so important to the scientific community? What is it about these entirely water-covered planets that interests astronomers so much? According to Li Zhang, a researcher at Harvard University, and his team, who classified the exoplanets according to their radius, 1/3 of the known exoplanets are ocean planets. They would thus be billions in the galaxy, and more than 1/3 of the exoplanets discovered would be covered with half water. The Earth is not the only blue planet in the universe. This is good news for astrophysicists who are looking for extraterrestrial life. Astronomers Raphael Luque, a postdoctoral researcher at the University of Chicago, and Enric Palais of the Institute of Astrophysics of the Canary Islands and the University of La Laguna have published an interesting paper in the journal Science. Their study focused on the occurrence of ocean planets around M-type red dwarfs, the most frequent stars in the universe. The conclusion of the study showed that ocean planets are surprisingly frequent around stars of this type. The search for oceanic worlds is important for the search for extraterrestrial life, because water is the origin of life, at least on our planet. This is why NASA is taking a close interest in Europa and Enceladus, icy moons of Jupiter and Saturn. Geysers have been observed on the surface of these moons. The objective of the next exploration missions will be to find molecules of biological origin in the particles spewed by these geysers. It is already known that these two moons have an ocean under an ice pack, and that they are subject to strong tidal forces that cause volcanic activity. This volcanic activity could imply the existence of hydrothermal hotspots at the bottom of these icy oceans. On Earth, these hot springs are home to many forms of life. In the absence of sunlight, it is chemosynthesis that allows living organisms to develop there. Let's look at this in more detail so that you can better understand why, like the icy moons Europa and Enceladus, the ocean planets are of interest to scientists. Water and energy are two essential criteria for the development of life as we know it. Ocean planets already contain water, so it is not surprising that they interest astrophysicists in search of an extraterrestrial life form. Especially if these ocean planets are located in the habitable zone of their star, i.e., neither too close nor too far away, so that the temperature, gravity, and pressure conditions are optimal. If it is proven that an ocean planet does contain water in a liquid state, all that remains is to determine a source of energy. The energy released by the planets in the form of heat can come from two sources: the tidal force or the decay of radioactive materials that compose their mantle and crust. The tidal force depends on the elongation of the orbit of the exoplanet. The decay of radioactive materials depends on the mass of its mantle and the age of the planet. Hence the importance, in order to refine the models, of being able to determine with precision the characteristics of the potential oceanic exoplanets observed. And then, is water and energy sufficient for the emergence of life? Planets can evacuate the heat produced by the tidal force or by the decay of radioactive materials via volcanism and tectonics. For a planet to be habitable, It must therefore have volcanic or tectonic activity, but not too much either. Let's get back to Li Zhang and his team. This researcher from Harvard University has used analyses from the European Space Agency's Gaia satellite to develop a new system for classifying exoplanets based on the constant RT for Earth radius. This new model makes it possible to explain the relationship between the mass, the radius, and the composition of exoplanets. A real step forward to better understand their formation and predict ever more accurate models. This new model shows in particular that the formation and the internal structure of planets are constrained by their dimensions. According to the system developed by Li Zhang and his team, planets with a radius of less than 2 RT are rocky and poor in water. Planets with radius between 2 and 4 RT are water-rich ocean planets. Between 4 and 10 RT, they are planets rich in gas. Beyond a radius of 10 RT, they are gas giants, composed mainly of hydrogen and helium. Li Zhang and his team have put forward an interesting hypothesis to explain the formation of ocean planets. These planets would have formed like gas giants, but would have eventually evolved differently to become water-rich planets. They are at the limit between a super-Earth and a gas giant, with a mass 8 to 10 times greater than that of the Earth. Ocean planets are numerous, but they are not all habitable. This is where the challenge lies in order not to get lost in endless research. We must know how to distinguish between those that are potentially habitable and those that are not. Ocean planets are interesting for scientists looking for extraterrestrial life, but not only. Even if they are not habitable and do not harbor life, they remain objects to be studied because they provide clues about the formation and evolution of planets, and thus of our solar system. Fasten your seatbelt. We are now going on a journey to the very heart of the ocean planets. What can you expect on this journey? Are the ocean planets similar to Earth? According to studies and models, ocean worlds would not be quite like the Earth, or even like Camino in Star Wars, but rather like the moons of Jupiter and Saturn, Ganymede, Europa, and Enceladus. Let's briefly recall the methods used by scientists to detect exoplanets, and therefore ocean planets. Exoplanets can be detected via the transit method, or via the radial velocity method. The transit method consists in detecting variations in the luminosity of a star when the planet orbiting it passes between the star and the observer. This is called a transit. The transit method allows us to deduce the radius of the exoplanet. The radial velocity method is the one used by the James Webb Telescope. This one embeds a spectrograph, which can highlight a Doppler effect. The Doppler effect is the apparent change in the frequency of a sound or electromagnetic signal from a moving object received by a fixed observer. This method measures the oscillation of a star in response to the gravitation of an exoplanet as the star moves towards or away from us. It works whether there is a transit or not. But if there is a transit, it is always better. This method would then allow us to determine the mass of the exoplanet, its radius, and therefore its density, which allows us to deduce its composition. Valuable information to detect ocean planets. These methods allow us not only to detect exoplanets, but also to know if they are gas giants or rocky planets. The observation of potential ocean planets with these methods has shown us that there would be a typical structure for ocean planets, which would be similar to that of the Jovian satellite Ganymede. Ocean planets would be composed of a core of iron, a mantle of ice and rocks, and a surface ocean, salty or not. How is an ocean planet formed according to scientists' models? Let's go back to the beginning of our solar system to better understand the mechanisms of formation of these aquatic worlds. The formation and evolution of the solar system is described by the model of the solar nebula hypothesis, developed in the 18th century by Immanuel Kant and refined over the centuries. Our solar system would be born from the gravitational collapse of a small part of a nebula. Nebulae are giant molecular clouds. The largest part of the cloud would have formed the Sun, and the scattered remains around the Sun would have formed the protoplanetary disk. This disk, composed of gas and dust, then served as a basis for the formation of planets, moons, and asteroids. In each planetary system, there is what is called the ice line. You may also hear it referred to as the ice line, frost line, or snow line. Whatever you call it, this fictitious line is the boundary between which a given chemical species exists in solid form. In other words, before the line, the species is in the form of gas, and after the line in the form of ice. There is therefore one frost line per chemical species, although this term is generally used to refer to the ice line of water. In the outer solar system, i.e., beyond the planet Mars, planetary objects are born from a structure similar to a comet, i.e., a mixture of water and rocks. They are then less dense than rocky planets. Their composition depends on their position relative to the frost line. Planets and icy moons that form near the frost line contain mainly water and silicates. And planets that form further away may contain, in addition to ammonia, methane, carbon monoxide, nitrogen, and carbon dioxide CO2. As the protoplanetary disk dissipates, the planets that formed further inside the disk will tend to migrate closer to the Sun. Planets that formed in the outer regions and migrated inward are more likely to contain abundant water than planets that formed near the star. A water-rich planet near its star was therefore formed farther away from the star before moving closer to it. The migration of icy planets to the interior of the star system involves the ice melting and becoming liquid, which transforms icy planets into oceanic planets. When a planet forms, much of the water in the planet is initially trapped in the mantle. As the planet cools, the mantle begins to solidify, and large amounts of water, between 60% and 99% of the total amount in the mantle, dissolves to form a vapor atmosphere. This atmosphere can condense to form an ocean. A heat source is therefore necessary to form an ocean. It can be, as you have seen, scientists are trying to establish models of the structure of an ocean planet once it is formed. The structure of an ocean planet depends on many factors and can be inferred from its density, shape, and gravitational pull. Studying an exoplanet can allow scientists to determine whether or not the celestial body has undergone differentiation, that is, separation into rock and ice layers. The small icy moons are made of a layer of water on a silicate core. In the case of Enceladus, the ocean is located between a solid shell of ice on the surface and the silicate core. Since the ocean is in direct contact with the silicates can provide hydrothermal and chemical energy to low-complexity life forms. But Ganymede, which is larger and contains more ice, has an even different and more complex structure. The pressures are high enough that there is an ocean between two ice shells. Imagine a sandwich with the ice instead of bread and the ocean as a filling. The filling of a sandwich is always composed of several elements or layers. This is also the case for Ganymede and the large ocean planets. As the pressure is variable at depth, water worlds may well have a structure that alternates phases of steam, liquid water, high-pressure ice, and plasma. Some of the water contained in ocean planets could take the form of Ice 7, a crystalline form of ice that is stable at high pressure. Let's stop for a minute to think about Ice 7, because it is a fascinating concept. This ice form was modeled by American physicist and Nobel Prize winner Percy Williams Bridgman in 1937. In 2017, it was observed directly in the form of inclusions present in diamonds mined at the Oropa mine in Botswana. These diamonds were formed in the transition zone of the Earth's mantle between 410 and 660 kilometers, or 250 and 410 miles deep, as liquid water subjected to very high pressures and temperatures. When the diamonds were brought up, the liquid water crystallized because of the drop in temperature, the pressure remaining about the same due to the rigidity of the diamond. The ocean of water worlds, thus trapped between two layers of ice, could be maintained if the ratio between the speed of internal heating and the speed of evacuation of the heat is favorable. The heating by the tidal force is thus a criterion of choice in the study of the oceans of these aquatic worlds. The one does not go without the other. Astrophysicists who study ocean worlds must also take into account these characteristics to better understand their structure, since they cannot go there to make direct observations. Smaller ocean planets of less than 1 Earth mass would have, according to the models, a less dense atmosphere and a weaker gravity. Liquid water could thus evaporate more quickly. But liquid oceans could be fed by hydrothermal activity, or tides, for example. Once again, a fragile balance that all potentially aquatic planets may not be able to maintain over time. Let's now move closer to an ocean planet to see what its composition could be. If we take the example of our Earth, water covers 70.8% of the planet's surface, but represents only 0.05% of its mass. The Earth is therefore not what we call an oceanic world. This percentage is much higher in the case of an ocean planet. For example, in the case of TOI 1452b, the first potentially habitable ocean exoplanet discovered in 2022, liquid water would represent 30% of the planet's mass. Does it surprise you that the oceans of oceanic worlds represent such a high fraction of their mass? Actually, it's not that surprising. Models suggest that watery planets have oceans so deep and dense that even at high temperatures, the pressure would turn the water into ice, allowing a mantle of complex ice forms like V-ice to form. V-ice is not necessarily as cold as the ice you know on Earth. Yet another fascinating form of ice. For liquid water on the surface of an ocean planet to remain liquid for long periods of time, the planet must orbit in the habitable zone of its star, also called the Goldilocks zone. Its gravitational attraction must be able to maintain sufficient atmospheric pressure to retain the water so that it does not evaporate into space beyond its atmosphere. According to the models, a powerful planetary magnetosphere is needed to protect the atmosphere from mass loss due to stellar winds and to retain the water. Either the atmosphere of a planet is formed by outgassing during the formation of the planet, or it is captured gravitationally from the protoplanetary nebula. It is the greenhouse gases of the atmosphere that will govern the surface temperature of an exoplanet. Greenhouse gases will also absorb and redistribute energy from the star around which the ocean planet orbits, which can give valuable clues about the composition of the atmosphere. The composition of a watery exoplanet and its atmosphere depends, among other things, on its position relative to its star. If the planet is close enough to its star for the liquid water to reach its boiling point, the water would reach a supercritical state. We speak of a supercritical state when water is subjected to high temperatures and pressures, but not to the point of becoming solid. If the ocean planet is colder, then the atmosphere could be much thicker than that of the Earth, and composed largely of water vapor, which could produce a greenhouse effect. The planet would then have to be small enough or close enough to its star for the hydrogen and helium to be volatile. Otherwise, it would be the equivalent of an ice giant, like Uranus and Neptune, but hotter. Icy planets that have migrated to the interior closer to their star could develop thick vaporous atmospheres and thus retain their volatiles for billions of years, even in the event of atmospheric leakage. Atmospheric leakage is caused by ultraviolet radiation and leads to the erosion of the atmosphere, as well as the eventual loss of the oceans. Indeed, atmospheric leakage also means leakage of water vapor, and therefore leakage of hydrogen and oxygen into space. Models estimate that the amount of water lost is roughly proportional to the mass of the planet. You have understood that there is not only one model of atmosphere for the ocean planets. On the contrary, there are many possibilities. However, because a general model must be developed, scientists have estimated that the composition of the atmosphere of an icy planet that became an ocean planet would be about 90% water, 3% ammonia, and 5% carbon dioxide. Now that you have understood how ocean planets are formed and what these watery worlds look like, you are probably wondering if life can develop on them. Can life forms be found on these ocean planets? Or even better, an intelligent extraterrestrial civilization? Are ocean planets inhabited, like the Camino planet from Star Wars? The first thing to know is that if the planet is entirely covered with water on the surface, then the development of terrestrial life seems unlikely. And if there is a layer of solid, pressurized ice between the liquid water and the rocky mantle, the development of life as we know it is even less likely. Scientists have addressed this issue by studying hypothetical ocean worlds. In the case of an ocean planet covered with 5 terrestrial oceans of water, it would not contain enough phosphorus for terrestrial ocean organisms such as plankton to develop. Plankton is an oxygen producer and therefore plays a crucial role in the oceanic ecosystem on Earth. On Earth, phosphorus, which is essential for its development, reaches the oceans through rainwater that has hit the rocks of the land. A mechanism that could not work on a planet entirely covered by oceans. Another simulation investigated the hypothesis of an ocean world containing 50 terrestrial oceans of water. The pressure on the ocean floor would be so great that there would be no plate tectonics. Without plate tectonics, there is no volcanism. And without volcanism, there is no chemical environment for the development of life as we know it on Earth. However, these observations do not mean that there can be no life on ocean planets. Small ocean worlds like Europa and Enceladus are considered habitable environments because the oceans are in direct contact with the silicate core. Now, the silicate core is a potential source of heat and can also provide chemical elements that could be the origin of life. In addition, according to some researchers, the thick underground ice sheet could be a means of transport for some ingredients of biotic activity. According to a study published in the scientific journal Nature Communications in June 2022, there could be exchanges between the core and the ocean, despite the presence of a thick ice sheet. Until now, scientists thought that this ice, type 7, was too dense and prevented any contact between the ocean and the core. But finally, this ice is not so impermeable as we thought, and it could bring some chemical elements to the surface. In addition, in 2021, a bioscience study led by Jeffrey Dick and Everett Schock of Arizona State University showed that organisms can thrive on the seafloor without light. This would also be possible on other planets, and thus in ocean worlds. On Earth, life is possible through a mechanism called cellular respiration, which involves the intake of oxygen and the release of carbon dioxide. But this mechanism does not work in the ocean depths without heat or light. This does not mean that there is no life on the seafloor. The study has shown that at the bottom of the oceans there are some specific hydrothermal environments that can harbor complex organisms. This is the case, for example, of hydrothermal vents or hydrothermal mounts, vents located on the axis of oceanic ridges that were formed as a result of tectonic plate movements. Around these vents, hot fluids mix with very cold seawater, an environment that may seem extreme, but is nevertheless conducive to the development and life of tiny organisms. When the vents are composed of ultramafic rocks, magmatic rocks that are very low in silica and produce a lot of hydrogen, this is particularly favorable for the biosynthesis of the basic elements of cells, like amino acids and sugars. Even more energy is needed for a reaction called polymerization, which will create larger molecules such as proteins. This study shows that even in a particularly inhospitable ocean environment, life can be born and develop. This gives hope to scientists who believe that ocean planets could harbor an extraterrestrial life form. If it exists, life on an ocean planet would be very different from life in our terrestrial oceans. For one thing, the oceans themselves would not look anything like our own. The oceans of these aquatic planets would probably be subject to violent storms. Cyclones would form and suck water vapor over the oceans, and since they could not lose their strength over land, they would cause huge waves of several tens of meters high. If there was life in the oceans of the water worlds, then it would have developed rather in the depths, in a calmer zone, or else life would not be easy. Now that you have understood what an ocean planet is, and that you have had a glimpse of what such a planet would look like, we are going to take a trip to the heart of the most famous ocean planets. On this trip, we will go as far as 219 light-years away. You will be able to observe Gliese 1214b, the first ocean planet ever discovered, and TOI 1452b, a potentially habitable ocean planet, discovered in 2022. You'll also see K218b, the first exoplanet in the habitable zone where traces of water have been found. And we'll explore multi-planetary systems like TRAPPIST-1, Kepler 62, and Kepler 138, which host several planets, including ocean worlds. Fasten your seatbelt and take off for the watery worlds of our universe. Let's start with Gliese 1214b. This is the first ocean planet that was discovered by calculation on December 16, 2009. This super-Earth, located at 40 light-years from us, is in orbit around the star, Gliese 1214, in the constellation of Serpentarius. Its mass is 5.5 to 7.5 times that of the Earth, and its radius is 2.6 times that of our planet. Its average density is low, 2 grams per cubic centimeter. To give you an idea, the density of the Earth is 5.5 grams per cubic centimeter. This ocean planet would be, according to the estimates, composed to 75% of ice and to 25% of rock and metal. According to this hypothesis, the ocean of ice would be 13,000 kilometers, or 8,000 miles deep, and the rocky core would have a radius of 4,000 kilometers, or 2,500 miles. Close to its star, GJ 1214b would have a surface temperature of about 200 degrees Celsius, or 392 degrees Fahrenheit. Its atmosphere is 200 kilometers, or 125 miles thick, and would favor a greenhouse effect. The presence of life as we know it remains unlikely. Observations of this planet have been made by the Hubble telescope's Wide Field Camera 3, the most advanced instrument on board the telescope to take images in the visible spectrum. According to these observations, Gliese 1214b would be a largely gaseous planet, with a high amount of water in its atmosphere. The atmosphere of the planet would be composed of 50 to 85% of water molecules. But how was the presence of water in the atmosphere of Gliese 1214b revealed? In a 2018 study published in the Astrophysical Journal, Japanese scientists demonstrated that the planet's atmosphere did contain water using 2 optical cameras on the Subaru telescope on the island of Hawaii. the scientists waited for the planet to pass in front of its star to analyze the light passing through its atmosphere. For this analysis, they used the phenomenon of Rayleigh scattering, a light scattering phenomenon that occurs when light particles are scattered without a change in wavelength. Installing a blue filter on the cameras of the Subaru telescope made it possible to determine the intensity of the Rayleigh scattering phenomenon. Since the scattering was weak, the scientists concluded that the atmosphere of Gliese 1214b is rich in water. But this conclusion must be refined because a weak Rayleigh scattering can also mean that the atmosphere is dominated by hydrogen and very cloudy. The observations also confirm that this ocean planet was initially formed far from its star, that it was rich in ice, and that it would then have migrated to approach Gliese 1214. Some of the water on this planet could be in the form of hot ice in an exotic state. The exotic state is one of the four possible states of matter, with a gaseous state, the liquid state, and the solid state. Or, water would form a supercritical ocean due to the temperature and pressure conditions. Supercritical water is obtained on Earth by heating water to temperatures above 374 degrees Celsius, or 705 degrees Fahrenheit, under a pressure of more than 221 bar. It is a powerful solvent for all organic compounds. If the oceans of Gliese 1214b were in a supercritical state, life would most likely not be able to develop there. Let's continue our exploration of the exoplanets most likely to be oceanic worlds. Located 100 light-years from Earth in the Dragon constellation, TOI 1452b is the most talked about oceanic exoplanet at the moment because it was discovered just recently, in June 2022. This exoplanet orbits a red dwarf star located in a binary system, which is smaller than the Sun. The two stars of this binary system are separated by 97 astronomical units, which is about 2.5 times the distance between the Sun and Pluto. TOI 1452b can be called a super-Earth because its mass would be equivalent to 4 to 5 times that of the Earth, and it would be 70% larger. TOI 1452b was discovered by an international team led by astronomers from the Université de Montréal. To discover this ocean planet so far from our planet, they used data from NASA's TESS Space Telescope. The main function of the TESS telescope is to observe the celestial vault in search of planetary systems close to our own. To do this, the telescope watches for minute decreases in brightness that are caused by the passage of a planet in front of its star. This passage is called a transit. The analyses of TOI 1452b estimate that 30% of its total mass would be water. The water could be in liquid form on the surface, since the planet orbits in the habitable zone of its star. Observations from the TESS telescope have also shown that TOI 1452b orbits its star in 11 days. To determine the mass of TOI 1452b, scientists observed the binary star system with a Spirou instrument that has been installed on the Canada-France-Hawaii telescope since 2018. The Spirou instrument consists of a high-precision spectropolarimeter, and velocimeter, and operates in the near-infrared. The objective of this instrument is to locate exoplanets located in the habitable zone of their star, but also to observe the magnetic fields of protostars, i.e., stars that are only a few 100,000 years old. The goal is to finally unravel the mystery of how stars are born. Spiru measures the minute variations in the speed of stars that are caused by the planets orbiting them. With this instrument, researchers were able to estimate the mass of TOI 1452b at about 5 times that of the Earth. According to all the observations that have been made since the discovery of this exoplanet, TOI 1452b is probably a rocky planet, but with a density much lower than what we expect from a rocky planet like Earth. Observations that make scientists lean in favor of an ocean planet. According to them, TOI 1452b would even be one of the best candidates for the title of ocean planet discovered to date. Separated from the Sun by a relatively short distance on the scale of the universe, 100 light-years, TOI 1452b does not cease to interest astronomers. The James Webb Telescope, launched in December 2021, should help them to establish an even more precise portrait of this ocean planet. Let's continue our journey to the heart of the ocean planets of our universe. Located 40.5 light-years away in the constellation Aquarius, the TRAPPIST-1 system has fascinated astronomers since the discovery of 7 exoplanets around the red dwarf star, TRAPPIST-1a. Not only because 3 of these 7 planets are located in the habitable zone of the star, and are therefore likely to harbor life, but also because such a number of planets in the same system could tell us a lot about the formation of our own solar system. Compared to our solar system, the TRAPPIST-1 planetary system has even more rocky planets in the habitable zone of the star than we do. Our solar system contains 2, Earth and Mars, and TRAPPIST-1 contains 7. The star around which this multi-planetary system is organized is an ultra-cold red dwarf, which is much cooler than the Sun, although it is more massive. It has a diameter of 11.5% that of the Sun, and a mass of 8%. It contains much more metal than the Sun, 109% more, according to scientists, and it can live 400 to 500 times longer, up to 4 to 5 trillion years. TRAPPIST-1a will certainly be one of the last remaining stars when the universe will be so old that the gas necessary for the formation of stars will be exhausted, and that our Sun will have disappeared for a long time. TRAPPIST-1 was discovered in 1999 by astronomer John Gizis and his colleagues. 16 years later, the Belgian telescope TRAPPIST discovered 3 planets orbiting this star. By crossing the information provided by the TRAPPIST telescope and those of other telescopes, 4 other planets were then discovered. These are the planets TRAPPIST-1d and TRAPPIST-1e, which are most likely to contain water in the liquid state, according to astronomers. They are neither the 2 closest nor the 2 farthest from their star. They are in fact the middle planets. TRAPPIST-1b and TRAPPIST-1c are closer to the star, so much so that Planet B orbits TRAPPIST-1a in 1.5 days and Planet C in 2.42 days, or 58 hours. TRAPPIST-1d is the least massive planet of the TRAPPIST-1 system. It has a mass equivalent to 30% that of the Earth. It is also the one which presents the weakest density and the gravity of surface. Its surface temperature is 9 degrees Celsius, or 48 degrees Fahrenheit. To give you an idea, the Earth's surface temperature is 15 degrees Celsius, or 59 degrees Fahrenheit on average. Separated from its star by 2.2% of the distance between the Earth and the Sun, it receives only 4.3% more sunlight than the Earth. TRAPPIST-1d orbits around TRAPPIST-1a in about 97 hours, or a little more than 4 days. Like TRAPPIST-1d, TRAPPIST-1e is located in the habitable zone of the multiplanetary system TRAPPIST-1. This planet has many points in common with the Earth: its mass, its radius, its density, and its surface gravity are approximately similar. The data collected show that its composition should also be similar to that of the Earth. Its average temperature is minus 27.1 degrees Celsius, or minus 16 degrees Fahrenheit, a little colder than Earth's. But since the planet is in synchronous rotation, it would be warmer in the part illuminated by its star, and water would be in liquid state, and on the contrary, colder in the unilluminated part, where it would be in solid state. So yes, the TRAPPIST-1 system has habitable planets, but can we observe ocean planets there? According to a 2018 study by Amy Barr, Vera Dobos, and Laszlo Kiss, TRAPPIST-1d could be covered with an ocean, while the outer planets, i.e. TRAPPIST-1f, G, and H, would be icy planets. However, because we have not been able to observe the TRAPPIST-1 system live, these remain guesses. Other studies show that according to their characteristics, and in particular their atmosphere, other planets of the TRAPPIST-1 system could be watery worlds. The planets F, G, and H could thus have an oceanic surface and a large core. TRAPPIST-1f is probably rocky, with a massive envelope of water vapor at very high pressure and temperature. It could therefore be covered by a thick ocean with an atmosphere rich in abiotic oxygen. Attention, it is not because there would be oxygen that it would be an indication of life. The abiotic oxygen comes in reality from sulfur dioxide. TRAPPIST-1g, the sixth planet of the multiplanetary system, certainly harbors water, since it is less dense but more massive than the Earth. If it has no atmosphere, it is surely an icy planet. But if it has a thick water vapor atmosphere, it could be an ocean planet. As its orbit varies little, it should offer a rather stable climate, rather favorable to the development of an aquatic life form. TRAPPIST-1h, the seventh planet of the TRAPPIST-1 planetary system, is even more distant from its star. It could harbor a subsurface oxygen heated by tides. There would thus be on this planet a strong activity of cryovolcanism, with erupting geysers, as on the moons Europa and Enceladus. Let's move a little farther away from Earth to examine a planet called K2-18b, which is located 124 light-years from us in the constellation Leo. This planet, discovered by the Kepler Space Observatory in 2015, orbits the red dwarf star K2-18 in 33 days and is located in its habitable zone. However, scientists believe it is unlikely to be habitable. K2-18b is 8 times more massive than the Earth. It is a super-Earth or mini-Neptune. In 2019, 2 independent studies concluded by cross-referencing data from the Kepler, Spitzer, and Hubble space telescopes that the atmosphere of this planet would contain significant amounts of water vapor. The equilibrium temperature of the planet is estimated to be about -8 degrees Celsius, or 17 degrees Fahrenheit, and it receives 94% of the stellar illumination that the Earth receives. Based on its size and density, it is unlikely to be composed entirely of iron and silicates, so it could be composed of hydrogen, helium, and ice water. In 2019, analyses of Hubble data by researchers from the University of Montreal and University College London examined the spectra of starlight passing through the planet's atmosphere during transits and concluded that K2-18b has a hydrogen-helium atmosphere with a high concentration of water vapor, between 20 and 50%. The water vapor could be high enough to form clouds. K2-18b was the first super-Earth discovered in the habitable zone of a star with a detected atmosphere. It was also the first discovery of water in an exoplanet located in the habitable zone. As a result of these observations, scenarios have been developed to determine possible models for this exoplanet. Several of these models admit that K2-18b could be an ocean world covered with liquid water and with temperature and pressure conditions similar to Earth. We will know more with the observations of the James Webb Telescope, launched at the end of 2021, and the Space Telescope Ariel, developed by the European Space Agency, which should be launched in 2028. The star Kepler-62 is much more distant than TRAPPIST-1 or even K2-18b. Located in the constellation Lyra, 1,200 light-years from Earth, it is an orange dwarf. At least 5 planets orbit it, including Kepler-62e and f, which are located in the star's habitable zone. In 2013, when they were discovered by the NASA Kepler Space Telescope, they were called the 2 most Earth-like planets ever discovered. Kepler-62e is a super-Earth, telluric like Earth, with a composition of iron and silicates. According to the hypothesis of scientists considered the most probable, it would contain an abundant quantity of water in addition to its rocky core. According to a modeling study of this planet, published in the Astrophysical journal, it is likely that the planet is entirely covered by an ocean. Kepler-62f is the farthest planet from the star Kepler-62, so it is located in the outer part of its habitable zone. It is 1.4 times larger than the Earth, so it is also a super-Earth. It receives as much solar energy as Mars, and the year lasts 262 days on this planet. Like Kepler-62e, it would be one of the first 2 viable candidate planets as a habitable zone ocean planet. A University of California study led by astrophysicists Omawa Shields, and published in 2016, estimated that the temperature of this planet would be compatible with the presence of liquid water. However, for Kepler 62f to indeed harbor oceans, it must meet a few criteria. The planet would have to have an atmosphere, 3 to 5 times thicker than Earth's, because its star heats less. This atmosphere, to maintain a temperature allowing the presence of water in a liquid state, should be composed largely of CO2. If, for example, the planet had an intense volcanic activity, it could maintain an atmosphere rich in carbon dioxide. And for it to be habitable, its atmosphere would have to be 3 to 5 times thicker than that of the Earth, as we have just seen. And in addition, the level of CO2 would have to be 2,500 times higher. What about the other planets in the Kepler 62 system? Astrophysicists have discovered 2 ocean planets, so they did not stop there. They investigated whether the other planets orbiting Kepler 62 could also be water worlds. Kepler 62b is the innermost planet in the multi-planetary system. It is about 30% larger in diameter than Earth and has an equilibrium temperature of 477 degrees Celsius, or 890 degrees Fahrenheit, which is slightly higher than that of Venus. No doubt, it is not an ocean planet. Kepler 62c is the second innermost planet after Planet B. It is about the size of Mars, but looks more like Mercury, the closest planet to the Sun in our solar system. It is therefore unlikely that this planet contains liquid water. Finally, Kepler 62d is not yet in the habitable zone, so it is too close to its star for water to remain in a liquid state. We end this journey with the planetary system Kepler 138. The star Kepler 138, or KOI 314, is a red dwarf star located in the Lyra constellation, 219 light-years from Earth. It is in the field of view of NASA's Kepler spacecraft, hence its name. In orbit around this star, 3 planets have been confirmed, and a 4th planet is likely. Kepler 138b is among the exoplanets whose size and mass have been measured, the one with the lowest mass. To give you an idea, the mass of Kepler 138b is similar to that of Mars. As for Kepler 138d, it has a very low density, so much so that it was long thought to be a gas dwarf planet, or mini-Neptune. A mini-Neptune is a planet whose mass is significantly less than that of Neptune, but which still shares some commonalities with this planet of our solar system. Mini-Neptunes have a thick atmosphere of hydrogen and helium over a deep mantle of water, ammonia, and other volatile compounds. If they did not have such a thick atmosphere, mini-Neptunes would actually be ocean planets. Recent studies from 2022 have shown that Kepler 138c and Kepler 138d are certainly watery worlds, with oceans 500 times deeper than those of Earth. They would also be warmer, with an atmosphere of hot water vapor. Let's go back for a moment to December 2022. Astronomers announced that they had identified the first true ocean planets, Kepler 138c and Kepler 138d. To reach this conclusion, astrophysicists compared the densities and masses of these planets with existing models And indeed, while these two planets are larger than the Earth, their density is nevertheless located between that of a rocky planet and that of a gas giant. To identify these oceanic worlds, astronomers use data from the Hubble and Spitzer space telescopes. The depth of the oceans of these two watery planets would be 500 times higher than the average of the terrestrial oceans. That is to say, a depth of at least 1,600 kilometers or 995 miles. Astrophysicists compared these two planets to Europa and Enceladus, except that Kepler 138c and Kepler 138d are larger and hotter than these oceanic moons. And instead of an icy surface, there would be large envelopes of water vapor. Kepler 138c and Kepler 138d constitute for astrophysicists the best evidence to date of the reality of oceanic planets, whose existence was theorized a long time ago. The oceans of these two planets would, however, be different from our terrestrial oceans. The available data show that they would be significantly warmer than our oceans, and that they would be under higher pressure. There may also be no clear boundary between the surface of the oceans and the atmosphere of Kepler 138c and Kepler 138d, which is certainly hot and composed of vapor. The temperature of this atmosphere is certainly above the boiling point of water. Under this hot atmosphere, there could be liquid water at high pressure, at depth, or in another phase like supercritical water. We have arrived at the end of this journey to the heart of the mysterious ocean planets. These aquatic worlds seem to come straight out of the imagination of a science fiction author. And yet, astrophysicists believe that it is more than likely that they really exist. What kind of creatures inhabit these extraterrestrial oceans? Are they microorganisms invisible to the naked eye? Huge prehistoric-looking creatures? Or ferocious creatures, like the Kraken of the fictional planet Mon Cala? Do these aquatic creatures have, as in our terrestrial oceans, a language to communicate between them? Do they inhabit the abysses of oceans more than 1,600 kilometers or more than 1,000 miles deep? Astrobiologists, astrophysicists, and astronomers are asking these questions and hope one day to be able to provide answers.